Let's graph logarithmic functions. Let's go back to something we talked about earlier. We said that y equals 2 to the x is the inverse of y equals log base 2 of x. We also know that you switch x's and y's when you go from a function to its inverse. Let's use that idea to learn to graph logarithms. We started our original exponential growth function by building this t-chart. How about we use this t-chart to help us build a t-chart that goes with y equals log base 2 of x? At the bottom, you'll see that I've reproduced the t-chart that went with y equals 2 to the x. Its inverse is y equals log base 2 of x. That will appear in my green t-chart above. So here's what I know. The first column of my t-chart shows that negative 2 comma 1/4 is on my original function. Reversing x's and y's means that 1/4 negative 2 is on the new function I'm going to graph. The second column says that negative 1 comma 1/2 is on the graph of y equals 2 to the x. That means 1/2 comma negative 1 is on the graph of y equals log base 2 of x. Now let's keep just reversing the x's and y's. On the third column I see 0, 1, so let me write 1, 0 on my new t-chart. Fourth column is 1, 2, reverse to 2, 1. Last column 2, 4, reverse to 4, 2. So I'm not yet thinking in terms of logarithms, I'm just thinking in terms of inverses. We will think more heavily about logarithms in the next lesson. So let's plot these points. 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, and 4 comma 2. If I plot a graph that passes through these 5 green points, I get my logarithmic function. Now, do you remember that functions and their inverses are always symmetric with respect to the line y equals x if you draw them on the same coordinate plane? So I am seeing that symmetry. The graph that was already there, by the way, was our y equals 2 to the x exponential growth graph. So, just like we did yesterday in the previous lesson, if you look at y equals 2 to the x, y equals 3 to the x, y equals 4 to the x, and so on, you're going to get the same basic graph with differences only in steepness. Well, I could do the same thing. I could say, well, how about I look at y1 equals log base 2 of x, y2 equals ln of x, y3 equals log base 3 of x, y4 equals maybe log base 5 of x. Just pick a variety. Now, the one thing you do notice is that I am increasing from 2 to e to 3 to 5 to 10. I'm just intentionally picking bases that are increasing. But when I graph all of those on the same coordinate plane, I see that I'm getting the exact same shape. The difference is in steepness, but there are characteristics common no matter what base you use for your logarithm. That means I can record the characteristics today just like I did for exponential functions. So if I say, all right, the basic shape of any logarithm whose base is larger than 1, and you're really only responsible for the ones whose bases are larger than 1. Like, for instance, I could graph y equals log base 1/2 of x, but that's not a common thing that we'll be doing. So if the base is a number 2 or larger, or actually anything larger than 1, then here's your basic shape. Now, What characteristics are shared regardless of the base? Well, there's an x-intercept this time. I'll even emphasize x-intercept is at 1, 0. I can see that there's a vertical asymptote this time, which overlaps the y-axis. So the vertical asymptote is at x equals 0. Now, the last time when we were talking about exponentials, the domain was all real numbers. Well, now you see that the range is all real numbers. And for exponentials that had not been transformed, the range was 0 to infinity. Now that's the domain. And I will be asking lots of questions about the domains of your various logarithms as you transform them. Just like with exponentials, what I want you to do whenever you're graphing these without a t-chart and without a calculator is show me 3 big things. Make sure that you are differentiating the logarithmic shape from the exponential growth and exponential decay shapes. So you've just got 3 basic shapes to deal with. Always dot the vertical asymptote in, especially if you've moved it off the y-axis. And always plot the intercept, even if that point gets moved around and would no longer be called an intercept. So for instance, when I'm looking at this, I'm going to go straight through what I did with exponentials. Let me say that my parent function is log base 8 of x. Whether the parent function is log base 2 of x or ln of x or log base 4 of x or log base 75 of x, the basic shape is the same. Now, the next thing I'll look at is log base 8 of x minus 5. This moves the graph right 5. First and foremost, you need to move the vertical asymptote right 5. So if you push the vertical asymptote right 5, you will see not only the intercept be pushed to the right 5, but the whole entire graph gets moved to the right 5. So you always, if you're moving the graph left or right on these, move the vertical asymptote first. Then finally, when you get to your final stage of graphing, the plus 5 on the caboose of this equation is a vertical shift. Therefore, the vertical asymptote doesn't do anything new, but you're going to see this point that is an intercept on the second phase get pushed upward to 6, 5. So it's no longer the intercept, but that is still the one point I'm wanting you to identify in the final graph. Now, something else I will typically ask you to do is name the domain of this function. Now that you have it graphed, do you see that it runs from the vertical asymptote to the right or from 5 to infinity? Now on the next one, I'm going to start trimming a little bit. I'm thinking, okay, the parent function is y equal ln x. Baby steps, they don't have to be perfect. Let me color code. If I address what the first negative does, remember if the negative follows immediately after the equal sign, you're looking at a vertical reflection. So that transformation turns the graph upside down, which doesn't change the asymptote or the intercept, but it does flip the graph. Last but not least, if I look at this negative, that blue negative is going to cause the graph to flip from left to right, or to reflect horizontally, or to spin about the y-axis. Lots of different ways you could say that. That does not change the asymptote, but it does flip the intercept and the shape of the graph. So there's the graph I want, and I'll fairly consistently ask you to name the domain. Do you see why the domain goes from the left all the way to the y-axis or from negative infinity to 0? I hope so. So let's do 3 more, and you will be ready to graph logarithms on your own, hopefully. My parent function is a logarithmic function as opposed to the exponential growth or exponential decay. I know the basic shape is a logarithmic shape. There's only one of those to know. The first thing I'm going to look at is the leading negative. That leading negative is a vertical reflection. So flip the graph upside down or reflect the graph over the x-axis. The next thing I'm going to do is deal with the x plus 2. That moves the graph left 2. First and foremost, pull the vertical asymptote from the y-axis and back it up 2. When you do that, the intercept backs up 2, and then the whole shape of the graph follows. Last but not least, the subtract 3 part at the end means move it down 3. The only way you can tell it goes down 3 is that the point that was the intercept at -1, 0 slides downward to -1, -3, and then repeat the shape. Name the domain. Do you see that it'll be -2 to infinity? Now, you certainly don't need to color code your graphs, and let me remind you that you also don't have to take the baby steps, but I'm going to show you that because, from my experience, students do better when they don't try to do everything at once, at least not at first. You may start doing everything at once pretty rapidly, but you're under no obligation to. So do what it takes to do well, even if that means doing a few baby steps. Now, I'm going to always start out with negatives. So I'm looking at my negative x. Since that negative's in front of the x only, it's a left to right reflection. So I flip the graph over the y-axis. Now, on the 3, this sometimes is hard for students, but remember that means that you are multiplying your y's times 3. There's not a lot to show here because the one y value that you have for this intercept, which would be -1, 0, the y value you have is 0. So even when I multiply that y coordinate by 3, it's still -1, 0. So what would happen is the graph is going to be a little bit steeper like this. But if you're not superimposing the vertical stretch over the unstretched graph, the average person can't show it well. So here's the deal. You don't have to. I'm only asking you to graph or plot one point on the graph. So on vertical stretches, don't really worry about them. Not a lot that you can do on those. I've named the domain, as I will, and you'll be asked to do quite frequently in your homework. Now, on this third one, y equals ln x, again, this is just a basic logarithm. I see that I have a shrink here of the 1/2. And again, if I vertically shrink the graph, then I could say the graph is going to be shorter. But if you're not superimposing the new graph over the original graph, you can't really tell it anyway. So my message is don't get too hung up on that because you're only having to plot one point. Now the +2 here on the caboose, remember that just means elevate the graph up 2. So the only thing that you can really show a change in is going from 1, 0 to 1, 2. Otherwise, there's not a lot to do on this graph. It just is lifted up 2. The domain has not changed because my vertical asymptote did not change. I didn't shove the graph to the left or to the right. So you're done. The next thing we'll get into is applications of exponentials and logs in the next video lesson.